About a parallel plate capacitor. We've used this in the electrostatics unit. Remember that it builds up a positive charge on one plate and a negative charge on the other plate. And also remember that like charges repel. If I connect the two plates together into a circuit, those positive charges are going to want to get away from the positive charges, and the negative charges are going to want to get away from the negative charges. So the net charge in each plate will decrease as the charges separate from each other. As these charges move, we're going to create what's called a current. A current is when charges move, and it is the electrons that move through a material. Ways that we can see a current are, first, we can look at the temperature. Anytime a current runs through a wire, the connecting wire will get warm. We can also know a current is taking place because we put something in the middle like a light bulb or some sort of resistance, and the light bulb will glow because it has a current flowing through it. We can also create a magnetic field by running a current through a wire, and we can see that magnetic field by putting a compass near a wire. We'll talk about that more when we get into electromagnetism. So what is it that creates a current? It's the difference in electric potential between 2 points. That's going to create an electric field, and that electric field will create a force on the electrons that makes them move through the wire. So if we think about two plates, we have a positive plate with a higher potential and a negative plate with a lower potential. This difference means that there's a different potential, so there's an electric field that's going to go from the positive to the negative. That electric field will cause positive charges to move the direction of this purple arrow, and negative charges, electrons, to move the opposite direction, and that will cause a current. The electric field makes charges move. The moving charges is defined as a current. We're going to talk in more detail about what happens in a current, but in general, you should know that current is conserved. The current that enters a light bulb is the same as the current that leaves a light bulb. This is similar to if you had a turbine of water. The water that comes in is going to be the same amount of water that comes out, and it's the same for electrons. The number of electrons that go into the light bulb equal the number of electrons that come out. So current is conserved. It does not change before or after a light bulb. And this is the law of conservation of current. The current is the same at all points in a current carrying wire. So our definition for current is it is a measure of the amount of charge that passes per unit time. The units we use, we're going to say it is the change in charge, or delta T, over change in T. And this is a capital I. I is what we use to represent current. So I is defined as delta Q over delta T, and this equation is on your AP Physics 2 equation sheet. So I is the current. It's measured in a unit called amperes. An ampere is equal to a coulomb per second. Q, or delta Q, is the change in charge. It's measured in coulombs. And delta T is the change in time. It's measured in seconds. So let's do a problem. Let's say we have an electric eel, and it discharges, and it can transfer a charge of 2 millicoulomb in a time of 2 milliseconds. What is the current of this electric eel? So we're just going to convert these into the standard units and solve for I. So milli is 10 to the negative 3 coulombs, and milliseconds is 10 to the negative 3 seconds, so it ends up being 1 coulomb per second, or 1 ampere of current. And 1 ampere equals 1 coulomb per second. So while we're using current, we also talk about an EMF, and batteries. So a continuous circuit is going to have a constant supply of charge running through it. And we can have two different kinds of circuits. We can have a circuit with an alternating current, or AC, and a direct current, or DC. For the AP Physics exam, we're only going to look at direct currents. Alternating currents are what you would get when you have peaks of current that it goes in a sinusoidal wave, but we're going to consider a direct current where it's a constant current. So DC current can come from a DC power supply or a battery, and this is the power supply we've used in class, or any battery can also give us a DC current. And the potential difference from the positive and negative terminals from here to here is called the EMF of the battery. It's also what we set on our power supply as our delta V. So delta V of a battery, this is the potential difference across a battery is the work that's done per unit charge in the battery. This is not an equation you have to know, but you should understand that the potential difference across a battery is the work per unit charge, and that is what we define our EMF. So EMF is equal to the change in potential across the battery. And inside a battery, the chemical reactions of a battery are doing the work to keep a higher potential at the positive terminal and a lower potential at the negative terminal. So they're doing work increasing the potential up the battery. We have the highest potential at the positive end. This is where we have a potential energy equal to charge times the voltage of the battery. And as you go through the circuit, our potential energy decreases, and then we get to the negative terminal where our potential energy goes to 0. And again, the change in potential across the battery is the work done by inside the battery per unit charge, and that's our EMF. The units we use for EMF are volts, capital V. So let's do another problem. Say we have 3 batteries connected one after the other as shown in this figure. We say they're connected in series. We're going to get to more detail about series and parallel circuits later. But what is the total potential difference across these batteries? So we're going to consider the work that it takes to go from this area which has 0 potential energy up to this part which has the maximum potential energy. And what is going to be the change in potential as we go through all of these batteries? Well, for this case, our potential is going to equal the sum of the total potential equals the sum of the potential of each battery. So we're going to add the potential from the first battery plus the potential of the second battery plus the potential of the third battery. And we get a total potential change in potential or potential difference of 4.5 volts.